Lecture 8.2, Diffraction Intensity Patterns. In comparing the intensity patterns of single versus two slit apertures, this is also openings, we find the following images. So what you're seeing here is that I have this pattern on the left, which is for single slit diffraction, and on the right we have two slit interference. So when I'm looking at the patterns, I'm seeing a pattern that's going to look something like this here. And let's say that this is the central one here. Is it? Or is this the central one? I don't know which one is the central one. Let's say that this is the central one right here. So what do we find? Well, one of the things that you see is that this guy has a very broad central max. So this guy is quite broad. And then if you start to look at these other ones, you can see here, maybe I don't have to do all of that, just trying to get the sense of where the width is at. So if I look at this width right here, there's width right here, width right here, and I might only do half of it. And I could just keep going on because you could see I can go all the way to the edge. And what you're seeing here is that this pattern is actually getting smaller in intensity. And then maybe I didn't do a good job on that. So let's say it comes here, it rises to the peak here, and then it has to go to 0 right here, and then it comes back up, and then the peak is smaller, and then the next one is even smaller. So when you're looking at this pattern, we'll have a broad central maximum, and then these smaller ones are called secondary maximas, and they get dimmer as you go out. So if you look at this as the relative intensity, you're going to find that in the central max here, this is 85% of the light is within the first central max. All of the secondaries get about 15% of the light. Now note, I should show that there's symmetry in this patterns here. Right, there's definitely symmetry in the patterns. Now, let's go look at these guys. So if I look at the relative intensity, what you're going to see here is to try to do this a little bit faster here. I'm going to take my peak and draw my peak something like this. And then I'm just going to copy and put them in. And in this one, it's important because all the peaks have the same height. In other words, they have the same maximum relative intensity. So then if I just start pasting these guys in, the pattern is quite different than the previous one. And so the key thing here is that you'll see here is that these guys all have the same relative intensity. So these are all the same max intensity, which is quite different than the interference. So let's write this down in words. So for single slit diffraction, the central max is much brighter than the secondaries. Regardless of the size of the aperture, that is the size of the single slit, the central max always has 85%, while the secondaries get the remaining 15% of the intensity. However, all two slit interference right fringes have the same max intensity. So, and here's another thing here. Two, I'm going to state, so stating this without proof, later on, it's actually easy to derive. The width of the central max is inversely proportional to the aperture size. In other words, if I look at the width of central max, this is proportional to 1 over the aperture opening. So in other words, if I have a small opening or aperture, then I'm going to have a wide, right? So then it goes like this. Then I'm going to have 1 over a squared. That implies that then I'm going to have a wide, that's not what I wanted to say, little a. Maybe I should do something like this. If I have a small a, I'm going to have a wide central max. Because now you can see here that this guy is going to be a tiny number in the denominator, which then means here that I'm going to have a large width to the pattern. On the other hand, if I have a large opening, then this tells me that I'm going to have a narrow central max. And that's because I have 1 over a squared tells me that the width now is going to be smaller. To show this effect here, I'm going to use the diffraction opening applet. And what you're seeing here is that I have a single slit, then I can adjust the opening of the width, and I can adjust the wavelength of the width. So what I'll do here is that I'm going to change it so that the width and the wavelength are the same. So in both cases, I'm going to have the same wavelength. So I'm going to take this wavelength and I'm going to make it as small as possible. Then I'm going to take the width and make it as small as possible. So what you're seeing here is that I have small waves that are going through an aperture that's the same size as the wavelength. And what you're finding here is that I'm getting a very broad central max. On the other hand, if I take the opening and I make it as wide as possible, what you're seeing here is that that central max here is more narrow. Okay, look how narrow this is. Look how wide this is. So let me go back to my screen and let me put in images, but these guys have different colors, but they look something like this here. So I clearly have used this applet earlier, and it turns out that it changes color. So now here's what I'm seeing. So what I need to do here is that I need to put in an aperture that's small versus large. So what I'll do here, let's say that this is what I'm looking at. So this guy's going to come here. And this one has a small aperture. And then my screen here is going to be right here. Now what I'm going to do here is that I'm going to copy this. And I'm just going to put it over here. And then I'll modify it so that we can use it how we want. So here we go. So what you're seeing here is that right here, you're seeing that my A value is quite small. So I have a small aperture or slit opening. And what you're seeing here, so if you look at the wave here, the intensity pattern, what you can see here is that this thing is quite broad. Very, very, very broad. In other words, I would say that this is wide. It's almost all the way across the screen. So then, if I was to try to draw this out, what I'm going to see here is that this guy looks something like this. So here's my intensity pattern. That looks like this. And so then I would say here is that from here to here, this is a wide width. Another thing that you're going to note here is that if you look right here, this is a lower intensity peak. Now, if you compare this guy, what we want to do here is that we want to create a wide aperture. So what I'm going to do here is that I'm going to make this wider. And so if I compare the size of this guy, you could see that the opening here, well, this is large compared to the other one. So here we have a large aperture. And as a consequence, we're going to have, so if you were to look at this peak here, you could see that the peak is essentially going from here to about right here. Now remember, 85% of the light has to be here. So then this is going to be quite large. And then I'm going to get really tiny minimas as they go out like this. We're not minimas, but maximas, secondary maximas. We don't care about them right now. All we care about is the central max. So what you're seeing in this situation is that we have this. I look at this here, and I see here that this is a narrow width. And another thing that you see is that the peak here, you have a higher intensity peak. And that's very the case for all diffractions. Okay, so the next thing I want to do here is that I want to go to the next thing. By the way, I did not draw this, but I should have. You could see here is that this is essentially the intensity. You could see how this guy right here is very wide, and this guy right here is very narrow. So now let's go on to the next step with the intensity patterns. What we want to do here is that we want to follow in the footsteps of part 2 above. Just what we completed. And what we're going to do here is that we're going to plot the intensities for various apertures. Now, this is an important step to physically understand diffraction patterns and how they behave. So here's the ranking of the apertures. One is that I'm going to rank them as like this. There's going to be 4 of them. And when you look at these 4, what you're going to see here is that this guy right here is the largest. This one right here is the smallest. Now, this is an image that I'm going to share with you, and it has a lot of stuff here. So this one is, in my opinion, an incredible graph. Okay, so the first thing you see is that look at A4. A4, and remember, we want to look at the width. So if I look at A4, you could see here that A4 has a broad central max compared to the secondaries. And then I have these secondary ones. And you could see that they're getting dim, but let's say that that's what you're seeing right there. And I'm only going to do one side. Now we go to the next biggest one, and this one is the orange one. And the first thing that you notice here is that its central max is definitely broader. And then you can see that the secondaries are definitely broader than these other ones. So in other words, this guy here is A4, this is A3. Then we get to the blue here, right? Blue, which is A2, and look how broad A2 is. So if I look at A2, it's essentially going from here to here. And then I get these secondaries that look like this. And again, this is A2. Now the smallest one is sort of like this fuchsia color, which I'm going to draw in violet. And it goes all the way across. And what we see here is that there's no minimas at all. And so this is A1. So if you're looking at this, the first thing that you should see here is that this one here has a very narrow central max. With highest intensity. Whereas A1, this guy right here, this has a very broad broad central max with lowest intensity. So summarizing what this picture is showing here is that if you have a large aperture, then you automatically have the highest peak intensity and you have the narrowest central max width. On the other hand, if you have the smallest aperture, then you have the lowest peak intensity and you have the widest central max. And all of diffraction has this pattern again and again and again. So it's a central feature. Now, another thing that we want to do here is that we want to look at the diffraction parameter. And the diffraction parameter, as we already said, is very similar to the interference parameter. So what we know here is that the diffraction parameter, which is equal to A over lambda, tells us about the number of minimas as well as maximas, since A over lambda is proportional to n, as we'll see. So in other words, if we have a large A over lambda term, then that means that we have more minimas. And if we have more minimas, that means here we're going to have a narrow, again, just as we saw, a narrow central max. With a higher peak intensity. On the other hand, if we have a small A over lambda, then that means we have less minimas. So therefore, we're going to have a broad central max with a lower peak intensity. So what I want to do here is I want to go back to the applet. So I'm going to go back to the diffraction opening. And then I'll come back with images to try to reinforce those ideas. So what we want to do here in each of these cases, what we want to do is we want to keep the wavelength the same, but change the opening in terms of 5 units. So let's go look at that. Wait, hold on a second. Okay. I am trying to find my applet to share. I'm not seeing it on my screen. I think you're seeing it now. And so remember, I'm going to keep my opening, or excuse me, the wavelength the same. So I'm never going to change the wavelength. So if you look at the wavelength, it reads 5 units, so it's only this guy. So now look what happens. If I look at the ratio of the diffraction parameter, that's 5/5, which is 1, and you see 1 central max. Now look what happens here. I'm going to go to 10. And look what you're seeing. You're seeing more diffraction. In other words, instead of 1 central maxima, you're seeing here that I have 2 maximas. There's the central, and then I have secondaries. So that diffraction parameter is a factor of 2, 10/5. Now, if I go to 15, I am now increasing the diffraction parameter because it's now 15/5, which is 3. And look how many minimas you're seeing. You're seeing 1, 2, 3. So there's more diffraction that we're actually looking at. And then if I go to 20, you'll see here that this diffraction parameter is 4, and I'm getting more minimas as a consequence. Now let's go back to our screen, and I have a different color, but it's the same thing, and it looks something like this. So instead of blue, this is yellow. So let's go look at this thing here. So the thing that we're really paying attention to is we're looking at the minimas here. So let's look at this. In this case, you could see here is that A over lambda is 5/5, which is 1. So if I look at the number of minimas, you can see here, I have a minima here, and I have a minima right here. So this is what we would call ND equals to plus or minus 1. Now let's look at what happens to these other situation. If I look at this, this is A over lambda, and this guy now is then going to be 10/5, which is 2. Look what's happening. I now have more minimas. And so what you're seeing in this pattern is that it looks like it's moving in this direction. So this would then tell me that this is now going to be ND equal to plus or minus 2. And you can see that I can keep going. I could have A over lambda in this case, which would be 15/5. I'm going to get 3. That tells me that ND has to be plus or minus 3. So I have to have 3 of these on each side. And in this case, looks like it's right here. So you could see that my minimas is increasing as the diffraction parameter is telling me. And so doing the last one, you're seeing here that now I have A over lambda. In this case, it's going to be 20/5, and that's going to be 4. So you could imagine now that ND has to be plus or minus 4. So I have to have 4 in each side, in each of these patterns here. So what I'm going to do here is I'm only going to do one side because I think you're catching on to the pattern that's starting to occur. And you can see that it's right here. And again, it almost appears like it's moving in this direction. It's pulling more minimas, if I could say that, right out of there. Now, one of the things here is that there is no such thing as a single slit. And what we really see is that we see what are called rectangular apertures. Well, not two P's, one P. So when I look at these apertures, here's what I want you to think about. So assume light impinges on a single slit. Well, let me try that again. Single slit. But these have two sides. So what people typically talk about, they go like, oh, we have a single slit. And we'll say, okay, I have a pattern that looks something like this. And then what we'll do here is that we're going to put in a single slit here, and everything else is opaque. So now what's going to happen here is that I'm going to say that this side here, I'm going to call that the horizontal slit, if I can imagine that. And so what's going to happen here is that I'm going to have light that's going to come in through this slit, and over here in the background, I have a screen. And what's going to happen to this screen here? Well, I'm going to get a diffraction pattern. So what I'm going to see here is that I'm going to see something that goes something like this. So what we're saying here is that what textbooks typically say here is that if I have a vertical slit, a vertical slit produces a horizontal diffraction pattern. But that slit has two sides, right? So if I was to really copy this guy here, what we're seeing here is we're actually seeing what? We also have a length to this, which we'll call B. So this is opposite. So this is really not a single slit, it's a rectangular aperture. So therefore, as light comes in, and I see my screen here, there are two patterns that are actually at work here. There's the pattern due to the horizontal one, which goes like this. But there's also a pattern vertically. So now what we're saying here, that if we have a horizontal slit produces a vertical diffraction parameter pattern. So now if we start to put this all together, so putting this all together, the diffraction pattern creates two superimposed patterns that appear as follows. So I want to show you two images. So here's what I'm seeing here. And you could see that in this case, I have a square, looks like a square to me. And you could see that there's two patterns. But when you put that together in the lab situation, you get something like this. And all that means here is this, that this guy right here, this one is due to the horizontal. Is it the horizontal? I always get that mixed up. Yeah, I would call this the horizontal slit. And then this guy would be from the vertical slit. The wording can get quite tricky. So now, following our applets from earlier, we could then ask the following question. Which aperture is square versus rectangular? So if you look at this thing, here's what you should be seeing here. Here's this pattern. And then we have this pattern. Now remember, when we're looking at which one's square and which one's rectangular, we're really thinking about what is this pattern really looking at as the diffraction parameter gets larger. You know that they have the same light, so what does that mean? So the first thing that I would say here is that note that these guys from here to here, they have equal spacings. On the other hand, well, let's finish this one here. So the spacings between minimas are equal, which then implies that A has to equal to B, and so therefore my aperture has A and B being equal to each other. So this is the square aperture. On the other hand, when we look at these guys, you could see that these guys right here, they have minimas. I should say that the minimas are farther apart. And if they're farther apart, that must mean that I have a smaller vertical slit. These guys right here, you're seeing that these minimas are closer together, which means they have a larger horizontal slit, or maybe not larger, how about slash wider horizontal slit. So in other words, in this case, we see here that since B is greater than A, then this is a rectangular aperture. There's even circular apertures. Yeah, there's even circular ones. So if I have a circular they behave the same as the square or rectangular apertures. So I could then ask this question. Can you tell which circular aperture is larger? Well, the two images that I'm seeing here, let me see if I copied it. Here's one image, and then here's another image. So what you're seeing here, the fact that these images right here, these guys are closer together. And then on this side, these guys are farther apart. So the fact that they're closer, that means here that this is the larger aperture opening, and therefore it has a brighter central max. On the other hand, the fact that they're farther, that means this has to have a smaller aperture, which then tells me I have a dimmer central max.